Good. Okay, afternoon. We are Team Google, and we are here to present our practical project. It was a CMU Google collaboration, and it's for interactive spaces, Google Interactive Spaces. Okay. So the nature of our project was to develop an application that would help basically help Google create engaging.
Sorry.
Yeah. So can you see it?
Okay, now it's switched. Okay.
Okay.
Delay. Okay.
Yeah. So we're basically trying to create and develop an engaging application using Google's interactive spaces and CMU's Spartacus project. Let's below that. Some of the text went out.
The resolution of the screen.
That was the resolution.
Yeah. Can you go to a lower resolution? Or you can just do it like that. Yeah, or just scroll through it like this.
Yeah.
Just click to scale.
No.
Just leave it out.
Yeah, it does leave it out. Okay. That's still here.
Mm-hmm.
Okay, yeah. So this project was done using Google's interactive spaces and CMU's Spartacus technology. And interactive spaces is basically something that was developed by Google. It's an open source project. It's a platform to help people connect with different devices or different applications within the same network or across multiple networks. It's just a way of messaging within a certain network between different devices. Okay, and Spartacus is an audio pairing system which uses Doppler shifts in high frequency sounds to recognize the change between one high frequency and the other. That way we can figure out where a sound is basically emanating from. Okay, we'll talk about that in detail later. Okay, so the interactive spaces itself was a collaboration between Google and Rockwell Divisions Lab. Google has an experience center in their Mountain View office, and a lot of the applications that have been developed on the interactive spaces were developed by Rockwell Labs. Right now, Google uses it for visitors to interact with some new type of technology, like a YouTube table, where you can search for a specific video and fling it to a wall, and things like that. It has a lot of nice, engaging applications. So, yeah. This right here is the system architecture of our overall project. So basically, we're meant to use the Doppler recognition part, that's the CMU Spartacus project, to track different displays, okay? So we decided to come up with an activity, which was the game that we developed. Decided to come up with an activity, and for that activity, we used the mobile recognition and the CMU Spartacus to basically tell where every display of the game was and to interact with the game. Okay, so this was the overall system architecture. We create sounds, or we emit sounds using the high frequency sounds using the beacon, and then the mobile device captures that high frequency sound and does some processing, which passes through the cloud, and it goes to the game that way. We'll go into detail with that later. Okay, now Hans will talk about this.
So basically, the Spartacus audio pairing system, basically it tries to do what NFC and Bluetooth does, but on a more natural, intuitive scale. So basically, the whole point is to find out what you're trying to share something with, or what you're trying to communicate with, like what device, which is in mobile context and computing context is a surprisingly difficult problem. So the problem with Bluetooth is you connect with anything in the room, so if there's a lot of stuff in the room, you have to scroll through this list to figure out what's what, and then sync with it, and it's this whole mess. And then the problem with NFC is you have to be close enough to actually touch something. So what this system does is you put an ultrasonic beacon next to like whatever conceptual thing you want to share with. And then with the phone, you gesture towards that beacon. And based on the Doppler shift, if there's multiple beacons in the room, you can tell which one you gesture towards. So basically, if you gesture directly towards the beacon, it's going to have a high Doppler shift. But if you gesture to the side or away from it, it's going to have a very low Doppler shift. So then you can compare through the frequencies that you're expected to have the beacons on and tell which one you gesture towards. So, and because of this method, there's no specific gesture that you have to use in order to be recognized. Basically, anything that produces a Doppler shift will work. So you can like stab at it, or throw overhand, or like underhand, or sidearm. Like all those methods work equally well as long as they produce that Doppler shift towards the intended target.
Is there a minimum movement?
Yeah, like we haven't really. It's actually pretty slow. Like I've done like that before, and it works just fine.
Okay, but
Like it's
is there a physical distance movement
No.
constraint? So even just a flick would do it?
yeah. Usually when I'm testing it, like I'm just like sitting on my laptop and just doing this. Like it's very short gesture.
Great.
As long as there's like some sort of Doppler shift, because like the audio sampling rate's way higher than your movements. It's all ultrasonic, so it's very short time periods. So even small movements are enough to recognize.
Are you talking about Spartacus or were you
Yeah. Well, both. What we have implemented works that way, and ours is based off the Spartacus system. So I'm talking about what we have implemented specifically. All right. Yeah. Okay. Yeah. Here's showing the gesture. So here's a sample from the Spartacus paper of one of the gestures that he tested with, and I tested with a number as well. So basically, there's this default gesture you use, and it's much more natural, a much more intuitive thing to do in an environment. All right, so here you can see the Doppler shift. So basically what you have is that you have your tone of, like if you do a frequency transform on the audio sample, you can see where the tones are. So there's gonna be this big spike where our beacons are. So then if you look at that, and when you do the gesture, it'll shift that frequency because of, just the Doppler effect. So we can actually look at that, and it'll generate a peak on a graph, and we look for that peak, and how far that peak is from the true tone value is how much Doppler shift there was. So if there's a high value there, then you're probably gesturing towards it. If it's like a low or even negative value, then you're gesturing like sideways or away from it.
Did you produce this figure as part of this project?
No, this is drawn from the paper, but we can show you some raw values.
Then
Like
you
in,
decide it.
there you go.
Then you need the citation.
Oh, okay.
We'll flip it.
Yeah, I can add this. I had a link to the paper like 2 slides ago. All the images are derived from the paper. Yeah.
So what kind of smoothing is done on that data?
It's a simple moving window smoothing, so it's a moving average.
Okay.
So basically, it just takes out the excessive piece.
So it's done in real time?
Yeah. Yeah, it's just very, very simple. And all right, so the beacon, basically each display or thing you want to interact with will have to have its own beacon on its own frequency. So these beacons, obviously, like you can't have any duplicate frequencies within earshot, or basically the detection levels of each other. So you're gonna have to have like if you plan on having a lot of devices in an area, you'll have to have a lot of frequencies and things of that nature. And basically, earshot is defined by like there's a threshold you can set inside the code, so you can play with that based on your needs and how like loud your beacon is and things of that nature. And the frequency, the code that we've tested our frequencies is from 19,500 to 20,500 hertz. So we've been using just simple like 500 hertz ranges between them just so to give us plenty of separation to work with. But you can play with this and make it smaller ranges if you want. It would just require a bit of optimizing in the code.
So our project was divided into 3 components basically. One was interactive spaces component, other was Hans audio Spartacus component. So my part was included was a cloud server, implement a cloud server, which basically gave like a connecting link between those 2 components. So let me see. So this was a cloud server. The main purpose, the main functionality of this cloud server was basically to relay message between interactive spaces and Spartacus. So this was basically a Java servlet, and it was also responsible for all the, we used Google Plus authentication. So the cloud server was also responsible for authentication and authorization of users. Because we were also using to display which user is playing, we fetch the Google Plus information after user signs in. Yeah, as I said, like it basically uses, it takes messages from Spartacus, like Spartacus is basically an Android application which will send the messages to interactive spaces. So it will take messages from that Android application, and the cloud server will like forward it to the Guillaume's application of interactive spaces. Can we just go back?
Bye-bye.
One more. Yeah, so this Google, I use Google Channel API. That is good for like we don't have to wait. The client doesn't have to wait for any messages to like come. Like it doesn't have to do the polling. Basically, it will just as soon as the messages as soon as the message comes from any of the user, the server is responsible to like broadcast to all the clients. Client communicator is basically the Android application, which is interface between Java, which is Hans library that was purely in Java, and then we had to interface with the JavaScript, the server page which my cloud server was displaying. So I used WebView to interface between JavaScript and Java, so that every time a user clicks a button, which will show in the demo, it will send out the frequency information about the frequency shift basically. Yeah. Now we will explain.
Okay, so the game was developed on the Interactive Spaces, and it was a measure of first demonstrate all the things that we're talking about, like with the Spartacus gesture, with the doubler shifts and everything. So the game basically is the aim of the game is to like have many displays displaying different colors and text, and you're meant to match the text with the color. Okay, it was seen as engaging anyway. We tried this out in Pittsburgh, and a lot of people actually enjoyed the game while they were playing it. They found out it was a really nice and competitive game, and we're going to quickly show you a demo of that pretty soon. This is how the game layout works, and this is how it interacts with the rest of the system. Okay? So we have the audio beacons that produces high frequency sound. Yeah, and each audio beacon is placed by a certain display. So we know, based on the display, we know which frequency to put, and we pair it up in the game. We say, okay, this display 1 goes with this frequency, display 2 goes with this frequency, and we know that within the game. Now the beacons send out high frequency sound, and each user that is using a mobile device picks up all the sounds that are being produced, all the high frequency sounds that are being produced, based on the gesture that they make to each display. So basically, if mobile 1 points towards display 4, 19,500 is going to, 19,500 is going to be the highest frequency, it's going to have the highest doubler shift. And then we know that he's trying to point towards display 4. And that's how we know, okay, he's interacting with the game. That message gets sent to the cloud server by the mobile ID. That's basically his Google Plus ID, so we can identify the player that's playing, and the frequency with the highest doubler shift, so we know which display is being pointed to. The cloud server sends that message back to Interactive Spaces system, and the game figures out which display is this person trying to point to, which player is making this interaction, and it says, did the player get this game? Did the player get the gesture right or wrong? Did the player get the screen match right or wrong? And then that message goes back to the display to say, you got this right, you got this wrong. So that's the overall flow of the game that we'll be demonstrating right about now. Okay?
Is this what you guys did for the inauguration?
Yes.
Yeah.
So,
Yeah. Nice.
Yeah. So we'll be demonstrating that right now.
Yeah, so I mean, we'll start set up.
Did you get other demonstration?
Yes. We still only have one beacon, but I can bounce between frequencies and show that it only picks out the right one. So.
What's the difficulty putting it into this real one?
What's that?
Putting it-
What is the difficulty of putting the gesture actually into this thing?
Into this?
Using the gesture instead of to actually score and stuff.
No, we can use the gesture.
We
now.
are
Yeah.
using gesture
Yeah.
only.
Yeah, I mean, so the way I coded it for both of them, just so we can demonstrate it both ways, this and the gesture.
So
Yeah, so we're going to use the gesture now.
It might not be, the calculations for the gesture will be accurate, but for the timings are still, like I didn't have time to optimize it. So it's still pretty slow in processing time.